All right, everyone. So here we're going to cover a different type of factoring. It's called difference of perfect squares. We're going to shorten that for DOPS, D-O-P-S. Sometimes you'll hear it also pronounced as DOTS, D-O-T-S, difference of two squares. But in this video, and I often call it DOPS, D-O-P-S. It means exactly as it says. It's going to be the difference of two perfect squares. And so let's take a look at an example of what that could look like. And then I'm going to break down the criteria of how do you know when to use difference of perfect square factoring. So here's what that looks like. It's going to be a binomial, okay, that has a subtraction sign. And you're going to have two perfect squares in that binomial. So it's going to be a binomial, meaning what is a binomial again? It is meaning an expression with two terms. It's going to have a subtraction sign. Okay. And it's going to have two perfect squares. Not one, but two. All right. That is my criteria. Sometimes you have to be careful. Some binomials will be very tricky. Whereas if you factor out a GCF, you can get two perfect squares. But you have to be very careful. You never know what you're going to be dealing with. So I'm going to give you those examples and just kind of do some run-throughs of how to factor it as well. So here you have how to identify it. And the better you get, you'll be able to do this. And then let's just jump right into the factoring, and we'll be able to take a couple of examples on. So that was my example over there. I'm just going to use the left side of our board here to do some DOPS factoring. Okay. So here's my example. Let me just write example. Okay. Here's our example. Alrighty. So you may see something like this. This is a DOPS problem. I know I'm going to use DOPS factoring because I have a binomial, check, two terms. I have a subtraction sign, and then I have two perfect squares. So I can then just quickly go ahead and factor this. So the way to factor it is you write two parentheses. Okay, you open up two sets of parentheses. You're going to put the square root of the first term inside of both parentheses. The square root of x squared is x, because x times x gives you x squared. Okay, now our sign. We have a negative sign here, right? So basically what we're looking at is negative 49. So another way to get negative 49 or anything, no matter what was on that right side, is that you need a positive and a negative. A positive times a negative will give you a negative. So whatever our next number is, we know that a positive times a negative will give us that. Well, what is the square root of 49? 7. So positive 7 times negative 7 gives you negative 49. Here you can see the clear example. And we're actually done here, okay? This is a very simple DOPS problem. So let's erase this and let's give it another go. Actually, one of the easier factoring methods, if you ask me. It's one of my favorites, actually. Let's give it another try. Let's give it another try with a very simple example. Okay. Binomial, subtraction sign, two perfect squares. I'm good to go. Let's change my colors up. Open my parentheses. Sorry for my parentheses looking crazy. Put the square root of the first term in both parentheses. For DOPS, you're always going to have a negative and a positive. Doesn't matter what order you write them in. And you're going to take the square root of the second term and put it in the parentheses as well. You're done. Okay. So here's another example. And you got to be careful because these examples do start to get a little tricky. But it's the same thing. You just have to know and get used to it. All right. So what if we had a 9 right here? Okay. And what if we had a 36 right here? Right? Does that change anything? It actually doesn't. Okay. 9x squared is still a perfect square. So is 36. So what is the square root of 9x squared? Well, that's 3, right? Because the square root of 9 is 3. Square root of x squared is x. I'm going to write that inside of both parentheses. Look at that. Okay? I'm always going to have a positive and a negative. It doesn't matter the order that I write it. And the square root of 36 is 6. And this is factored, okay? So remember earlier I was talking about those examples where you want to look for the GCF first, just because it's a good habit to check for the GCF, because when you have some problems that have greatest common factors, you won't know until you take out the greatest common factor that you can actually use DOPS to factor it, right? So let me give you one of those examples. All right. So let's take a look at this example. 5a squared minus 45. Now, in your head, do you think that this is a DOPS problem? Well, I have a binomial, 2 terms. I have a subtraction sign. But these are not perfect squares. No number times itself gives you 5. No number times itself gives you 45, right? But we know it's a binomial, right? So that's, you would start thinking, do I use DOPS? Do I not? But if you take out the GCF, if you factor out the greatest common factor first, you will be working with a DOPS problem. So it is also important to take a look at what you got and possibly see if you can get a greatest common factor other than 1 out of your binomial. So what's the greatest common factor between 5 and 45? The greatest common factor is 5. Let's use red. Okay, the greatest common factor is 5. Okay, so now I'm gonna open up my parentheses. Okay, so all I did was factor out of 5, because that's the only thing they have in common, and I'm just gonna rewrite the rest of the problem. A squared minus 9. Now what do you notice inside of this parentheses here? I have 2 perfect squares. A squared, right? And that would normally be x, so that's fine. A squared is a perfect square, so is 9. And I have my subtraction sign. See, this is where DOPS gets pretty interesting. If you factor out the GCF first, sometimes, depending on what you have, then you'll be fine. Okay, so we couldn't factor out a GCF here because if we would have, we would have just ended up with the same thing, right? The only thing they share in common is a 1. But this is very different. Okay, they share a 5 in common, and then it creates a difference in perfect squares expression, okay? A binomial with 2 perfect squares. So how do we factor that? Well, we do the same thing we just did, okay? We write our 5, and then we factor by opening up 2 sets of parentheses. So, right, we're factoring it all the way. Square root of the first term, both parentheses, okay? We know we got a negative and a positive, always for DOPS. Square root of the last term, 3. Boom. Okay, and this is completely factored, so even your difference of perfect square problems can look very different. You just definitely want to check for that GCF as well. Check for those perfect squares, and make sure you have a subtraction sign and you're good. So for example, one last example. Gotta know what you're looking for. Gotta know what you're looking for, okay? And you'll get comfortable the more you do. This is not a DOPS problem. Simply because it disobeys our second rule. There's no subtraction sign, okay? So you would not use DOPS to factor this, okay? And so be very careful at what you have, because if it doesn't meet your criteria, you cannot use anything to factor that, all right? You may have to use something different. Also, you'll see DOPS problems come like this. This is another common way I've seen it on the Regents. X to the 4th minus, let's say, they'll say 16. And this is very simple. You'll set it up just like a normal DOPS problem, but you'll just notice that the square root of x to the 4th is x squared, okay? And that's the only difference. Sorry if I'm a little sloppy here, okay? And that's it. That's it. Most DOPS problems are probably going to look like a variation of what you've gotten. And yeah, I'll give you one more example to see if you can give it a go. Actually, two more. Alrighty, let's do it here. Let's go been using that one quite a lot, actually. Let's go with 25x minus 144. And then let's go with x. Yeah, let's go with another one. Let's go with one where you got to get that GCF out. This one's a little tricky. It's backwards, isn't it? Right? But it still meets our criteria. We can see what we can do here. And we can see if we can factor this out. So go ahead and give it a try. See what you can do here. Pause the video and then give it a try and we'll get back. Alrighty, so we're gonna open up our sets of parentheses because I notice I have binomial, subtraction sign. Both of these are perfect squares, so I can go ahead and just start to factor this one very easily. Oops, this is supposed to be x squared. So 5x and 5x, right? This is so tight. Let me erase this. All right. Okay, one positive, one negative, doesn't matter the order. And the square root of 144 is 12. So you take the square root of both terms, positive, negative, boom. Okay? Here now, the only interesting thing here is 63 is not a perfect square, nor is 7x squared. So maybe I'm thinking, let me check for GCF. If I can take a greatest common factor out, then maybe it'll leave me with a Dobbs problem. And it will. The greatest common factor of 63 and 7 is 7. Okay, is 7. They don't share anything else in common. So therefore, I'm left with x squared. Let me write it in the way that you see it, actually. I'm left with, get that out of there, left with 9 minus x squared, okay? So I know it's like, oh, this is backwards, but they just do many different things to try to trip you up. It's the same thing if it was reversed, but you still have two perfect squares after you found the GCF, and then you would further factor that. 2, 3 minus x, and we are done. Just take the square root of both of them, and you rewrite it again. Sorry. Now we're done. Yeah, almost did a different type of factor. So, yep, we are good here, and just get used to what you're looking for, and you'll be good to go.